Alright, so in the last video we talked about periodic trends and electron shielding and atomic radius. In this video we're going to talk about ionization energy. And to understand ionization energy, we're also going to need to think about electron shielding, and it's also closely related to atomic radius. So first of all, we need to talk about what ionization energy is. So ionization energy is the amount of energy that's necessary to remove an electron from an atom. So we're talking about the energy associated with the reaction of going from a neutral atom to a +1 ion by taking an electron away from that atom. And we can talk about successive ionization energies, right? The first ionization energy is the electron required to take the first electron away. The second ionization energy is the energy required to take the second electron away. So we're starting from the +1 ion, we're going to take another electron away and make the +2 ion. And we can keep going, right? We could take all of the electrons away from an atom if we had enough energy. And so the third ionization energy would be starting from the +2 ion, and then we'd be going to the +3 ion and taking an electron away from the +2 ion to give us the +3 ion. And so this would be the third ionization energy, or IE3. All right, so what are the trends in ionization energy? So we have two groups of the periodic table. We have the alkali metals, shown here, and we have the noble gases. And in both cases, you can see the same trend. As we go down the periodic table, the ionization energy, and this is the first ionization energy, the ionization energy decreases. And that's true for both cases, right? So what that's telling us, as I go down the periodic table, it's easier to remove electrons from an atom. And that's directly related to the atomic radius. We also know that as we go down the periodic table, the atoms get larger. And so the valence electrons are further away from the nucleus, and so it's easier for us to pull them off. It doesn't require as much energy to remove them because they're more distant from the nucleus. Another interesting thing to point out, the ionization energies of the alkali metals are fairly low. And that might make sense, or at least compared to the noble gases. And that might make sense because we know that alkali metals, when they form ions, they like to form positive ions. So it must not be very hard to take their electrons away compared to other elements, right? In noble gases, it may not be surprising that they have relatively higher ionization energies because they have completely filled subshells. And when we talked about electron configurations, we talked about how that's particularly stable. And so the noble gases really don't like to give up their electrons. And so they have relatively high ionization energies, at least compared to the alkali metals. So we've talked about what the trend is in ionization energy as we move up and down a group in the periodic table. But what about when we move across a period, when we go from left to right across the periodic table? Well, you can see in general, right, so here's lithium through neon. So this is the second period, and we can see the general trend is very clear. The ionization energy increases as we go from left to right across the periodic table. And that's true for all of the periods. Although you can see, right, the general trend certainly holds, but there are also certainly some exceptions. And we'll talk about what gives rise to them in the last couple slides. But the general trend, at least, we can understand with electron shielding and effective nuclear charge. As we move from left to right across a row of the periodic table, the effective nuclear charge increases, right? The electron shielding decreases because the charge of the nucleus is getting larger, but the number of core electrons is staying the same. And so, for the same reason that the atoms get smaller as we move from left to right across the periodic table, the electrons are more tightly held, and so the ionization energy also increases. All right, so the general trend in ionization energies as we go up and to the right in the periodic table, the ionization energy increases. From the last video, the atoms get smaller, and the ionization energy, the energy required to take an electron away from an atom, increases. Now, when we looked at that chart that showed the ionization energies of a lot of the different elements, and we looked at what was happening as we went across period, we saw that there were a couple exceptions. There were a couple dips, and it wasn't just a straight up increase. And so I think it's helpful to understand what's giving rise to that. And so if we think about the second row of the periodic table, we have lithium and beryllium, and then boron, carbon, nitrogen, oxygen, fluorine, and neon. And two of the exceptions happen in between beryllium and boron, and then in between nitrogen and oxygen. And so to understand what gives rise to these irregularities in the trend, it helps to think about their electron configurations. So the ionization energy of boron is actually less than the ionization energy of beryllium, right? And that's backwards based on our trend. As we go left to right, we would have expected boron to have a higher ionization energy than beryllium, and it does not. And we can understand that if we consider the electron configurations. And the same thing happens with nitrogen and oxygen. So let's talk about beryllium and boron on the next slide. So when we talked about irregularities in electron configurations, right? Copper was one example. Its electron configuration, its outer electron configuration is 4s1 3d10. Because by promoting that electron from the s orbital to the d orbitals, we can get a half-filled and a completely filled subshell. And that's because completely filled and exactly half-filled subshells are particularly stable. And so that also explains why beryllium has a higher ionization energy than boron, even though that goes against our trend. Right? Beryllium's outer electron configuration is 1s2, 2s2. And so all of its subshells are completely filled. When I go to beryllium plus, I have to take away one of those electrons. And so now it no longer has a completely filled subshell. So it's going from a particularly stable electron configuration to one that is not particularly stable. So it doesn't really want to do that. So it resists it more than we might predict just based on our left to right trend and just based on effective nuclear charge. Boron, on the other hand, it goes from its 2p subshell being neither filled nor half filled, and so that's not especially stable. It's not a special configuration. But by taking an electron away, all of its subshells are completely filled, and so it kind of likes that. So it always requires energy to remove an electron from an atom, but it costs a little bit less to remove an electron from boron than we might predict just based on effective nuclear charge. And so because of this, boron actually has a lower ionization energy than beryllium, and that's why it bucks our regular trend. And a similar thing happens for nitrogen and oxygen. Nitrogen's outer electron configuration is 1s2, or its complete electron configuration is 1s2, 2s2, 2p3, and so its 2p subshell is exactly half filled, which it kind of likes. When I go to nitrogen plus, it's no longer completely half filled, and so nitrogen doesn't particularly want to do that, even more than it would normally like to lose an electron, based on effective nuclear charge. We also lose a favorable electron configuration. And oxygen, its outer electron configuration is 2p4, right? That's not filled or half filled. When I go to oxygen plus, it gets to have a half filled subshell. And so while it still costs energy to remove an electron from oxygen, it costs a little bit less than we might expect just based on effective nuclear charge. And so it's due to the special stability of half-filled and completely filled subshells that give rise to a lot of the exceptions that we see in the ionization energy trend. Okay, the last thing I want to talk about is successive ionization energies. And so every time I go to take another electron away from an atom, it always costs more energy. It's always easiest to remove the first electron. The second electron takes more energy than that. The third electron takes more energy than that. And that's always true. And we can understand that if we think about a neutral atom. So let's do something easy like lithium, something small. Right? Lithium has a +3 charge, and then it has 3 electrons in the electron cloud. For the first ionization energy, when I'm pulling off one of these electrons, when I'm pulling it away, right, so this electron is coming off, I'm separating a negative electron from what is effectively, right, the ion that I'm leaving behind is a +1 ion, right? I still have 2 electrons to be -2, but I have a +3 nucleus, and so this ion overall is going to be +1. And so I'm removing an electron from a +1 ion, and that requires energy because that electron is attracted to that +1 ion. For the second ionization energy, however, when I go to remove the second electron, right, now I'm taking that electron away. What it's leaving behind is a +2 ion. And so now I'm taking a negative electron away from something that is +2, right? It's really attracted to that +2 ion, and so it requires even more energy to take that second electron away. And then it's even more true for the third electron. When I try to take the third electron away, that would be taking it away from a +3 charge, and so that's even harder. So every time I take away another electron, the ionization energy goes up. So the second ionization energy is always bigger than the first ionization energy, and so on. Now, one of the things that we can use successive ionization energy for is to understand something about atomic spectroscopy. So spectroscopy is something that we'll talk a lot about throughout your chemical careers, and it has to do with how different atoms interact with, in many cases, electromagnetic radiation, and how much energy is required to excite vibrations, or to move electrons into different energy levels, or to remove electrons completely from an atom. And so if we look at successive ionization energies, another thing that happens, not only does it increase every time we take an electron away, and so here we're showing for sodium and magnesium the successive ionization energies, right? And in both cases, the first ionization energy is the smallest, the second ionization energy gets bigger, the third ionization energy is bigger still. But you can definitely see some differences here. There's a big jump between the first ionization energy and the second ionization energy in sodium, and the big jump doesn't occur in magnesium until we go look at the second and the third ionization energies. And what's going on here is the difference between the ionization energies of core and valence electrons. Right? We know that core electrons are in a smaller shell of the electron cloud than the valence electrons, and so the core electrons are closer to the nucleus than the valence electrons, and so they are much harder to remove. In the case of sodium, it's an alkali metal. It's in the first column of the periodic table. It only has one valence electron. After I take that one electron away, the other electrons I'm removing are core, and so the valence electron pops off relatively easily. But then the second ionization energy, I'm trying to take away a core electron, and that requires much more energy than it did to remove the valence electron. Magnesium is an alkali earth metal, so it's in the second column of the periodic table. So it has 2 valence electrons. So while the second ionization energy is higher than the first, there's not a huge jump. But then when I go to the third ionization energy, at this point I've already taken away the 2 valence electrons, and so now I'm removing a core electron, and so now we see the big jump in successive ionization energies. And so this is a way that we can identify atoms, right? Each atom is going to have a characteristic series of ionization energies, and we can use that as a tool for identifying what atoms we have. And so if we look at an example, so I have, in 2 different cases, I have some successive ionization energies. So we've got ionization energy 1, 2, 3, 4, 5, right? So how much energy is it required to take off the first, second, third, fourth, and fifth electrons in both cases? And so we're told that this is a period 2 element, and we want to identify it. So what we're looking for in these successive ionization energies is, where is there a big jump, right? So we have an increase when we go from 1 to 2, we have another increase when we go from 2 to 3, and then we go from 3 to 4. Holy crap, right? Like, we're going up by a couple thousand, and all of a sudden we're going up by more than 20,000, right? So the big jump is between ionization energy 3 and 4. So what that tells me, right, is that the ones that were easy to take off, the first 3, These are my valence electrons, and now I'm starting to get into the core. So if we go to a periodic table, right, we're in period 2. The first 3 were easy to take off, so I have 3 valence electrons, and the rest are core. So in period 2, the element that has 1, 2, 3 valence electrons, that would be boron. All right, and if we look at the second example, we've got 738, we've got 1450, and then now we've got a big jump, right? The jump is about over 6,000 between IE2 and IE3. Before that it was less than 1,000. After that it was about 3,000 difference. So this is my big jump in the second example. So this element has 2 valence electrons. If we're in period 3, this is going to be magnesium. All right, so there's one more video on periodic trends, and that is sort of the opposite of ionization energy. We're going to talk about electron affinities.